Okay, we're back from the break and we're looking at propagation of signals on integrated circuits. So the first thing we'll look at here is some distributed RC effects, and this might just be a representation of a long line. Perhaps it's a copper metal line over ground, and that'd be separated by a dielectric like silicon dioxide. And this is an equivalent circuit, and basically we're interested in things like the voltage at this point and the current flowing through the wire at this point, and sort of represented by these variables here, ij minus 1, ij, and vj. The important point is that the distributed RC line model, the R is in ohms per meter or something similar, and the capacitance is in farads per meter or something similar. Some of the delta x's are not shown on this figure because I got a little lazy. Anyway, you can end up writing KCL at node J quite simply. Just the current in is equal to the current out of that node, and we can represent the current going in as just a difference in the voltages across that resistor, the current going out, the difference in the voltages across the resistor adjacent to it, and then the current flowing through the capacitors, the C dV dt, where this is the infinitesimal amount of capacitance associated with that little segment. Because remember, C was in farads per meter. So that's just rewriting this equation, and we see that we get a difference in voltages over a difference, and we're going to be able to, quite quickly see that that's our second derivative, and we get a nice little diffusion equation, which is just the RC dV dt equals the second derivative voltage with respect to x. And this is obviously the describing equation. The solutions are probably a little bit difficult to come up with, but certainly well known to be a function of time would be a function of x squared. And we'll sort of see what that means in a minute, where k would be, let's say, the diffusion coefficient, x position, and time would just be the propagation delay down the line. And that's typically going to be represented at a particular value of voltage. So this is in-class assignment 5 star. Basically what you're going to do is either describe how I did the simulation or describe it for yourself. And to do it for yourself, if you're so inclined, it's quite simple. And it's just a simple model of diffusion where here a couple of plots are generated here, where this is time and the value of x when the voltage was at its 50% value as it sort of moved along. These are different times, and this would be the voltage profile. And as you can see, there's a pretty good fit to a quadratic. These terms kind of die out quite quickly, and I probably didn't take enough care at the beginning here. It would have been closer, but our r squared coefficient is equal to 1, which means we have a pretty accurate fit there. This blue line is directly over top of the fitted line. This is what it looks like if you're looking at the voltage as a function of x parameterized by time. And here's a couple of things to point out. For example, at time t equals 250, that's that red curve there, the value of x is exactly equal to 10. And when t was equal to 1000, which is 4 times later, the value of x is only doubled and it was equal to 20. So you can see that you get that quadratic dependence. Here's a back of the envelope distributed calculation. Might be a little bit clearer for some people who like a discrete version like this. And we just look at that Elmore delay. And that's the delay we looked at previously in a couple of examples. And we just see that the delay associated with that input to output is just going to be basically charging or discharging these capacitors one after the other, and they charge or discharge through different numbers of resistors. So for example, this first C1 is only charged up through R1, C2 is charged up through R1 and R2, C3 is charged up through R1, R2, and R3, etc. So we end up with a simple little equation that we can calculate the delay for. And what we'll see that evaluates out to is a simple little sum where we can pull the Ci and the Ri out of the summation, and we're just going to sum I from I equals 1 to n, where there's n of those little segments. So we'd end up with an expression that looks like this, Ci Ri n squared over 2, and then we just rewrite the Ci and Ri in terms of the capacitance per unit length and the resistance per unit length. It was of length n and length L, and it was divided into n little segments. So these n's all cancel out, and we get an L squared Rc over 2. So L was the length being divided by n segments. R and C were the resistance and capacitance per unit length values. The observations, again, is quadratic in length as expected, and 1/2 of the delay associated with the lumped approximation. So if we would have just gone to the trouble of saying, let this capacitance be equal to all of those capacitance summed together, let this resistance be the resistance of all those summed together, we'd still only be out by a factor of 2. So this also leads us to believe that this isn't the most accurate calculation, but probably better than the initial lumped one. So if you're looking at some real interconnects, for example, you might consider an inverter driving another inverter over a long line, and then we'd basically ask ourselves what the time of flight is, or the propagation across that interconnection. We're going to have to do some estimates here. So let's say we don't know anything else. We're going to at least have a maximum speed for the propagation of 3 times 10 to the 8 meters per second, and we're going to compare that to the inverter rise and fall time. If the time of flight is very short, then we could just model that as a capacitive load, or perhaps a lumped RC kind of network. But more than likely, the resistance here is going to be that governed by the inverter. If the interconnect lines are sufficiently long and the rise and fall times are less than or comparable to the time of flight across the line, then inductance may also become important, and the interconnection line should be modeled as a transmission line. So this is sort of an initial rule of thumb to help us determine whether we should consider that line a T line or not. And if the fall time is very short compared to the propagation time, it sort of leads us to believe we should consider it a transmission line. Here's another example. If we use the speed of light, sort of that being allows us to calculate the time across a trace, and we had the speed of light at 3 times 10 to the 8 meters per second, maybe a chip dimension which is 3 centimeters on a side, which is an extremely large chip, probably a trace you never actually see. The time of flight in that case is 3 divided by 3 times 10 to the 10 centimeters per second, or basically the time of flight is going to be 0.1 nanoseconds. So that brings us into the regime of signals which are on the order of 10 gigahertz or so. So if we're much below this, then we probably don't have to think of it as a transmission line. If we're a little above this, we probably have to begin thinking of that trace as a transmission line. The other factors that come into play: signals don't travel at the speed of light, maybe 30 or 50% of the speed of light, so that refines that calculation. So the point being that in the gigahertz regime, transmission line effects may become important. And we saw that very early on when we were looking at some of these clock distribution networks, and hence all the design effort with the clock tree synthesis. And that was primarily also to make sure that signals were, arriving at roughly the same time, so that we don't have a clock skew on the chip. Here's another example for a propagation versus a propagation or time of flight, let's call it, and the rise and fall times. A little bit more accurately here, we're going to estimate the velocity of the signal to provide us with the time across a chip, and the velocity is basically the speed of light divided by the square root of the permeability times the permittivity. And this equation is attributed to Maxwell. It's sort of electromagnetic wave going through a medium with a permittivity and a permeability, which is different than air. So in that particular case, these values happen to work out to about half the speed of light. So we're working with 1.5 times 10 to the 8 meters per second. Maybe not an unreasonable chip dimension now. It might be 1 centimeter on a side. So that's a trace that's going across the chip. And in this case, the time of flight is 66 picoseconds, but the rise and fall time of the inverter could easily be on the order of 10 picoseconds. So here we see that we should probably be thinking of that trace as being that of a transmission line. And in this case, transmission line design would be required for that trace, and a lot of care would have to be perhaps provided for the termination of the source and the receiver. And here's a website that sort of has some information on terminating impedances. This is more, I think, for a printed circuit board, but many of the same concepts apply. And at this point in time, we'll take a brief break.